Hello, welcome to Basics of Finite Element Analysis Part 2. Yesterday we had introduced the notion of numerical quadrature or numerical integration, and we had seen two integration methods. One is the trapezoidal rule and the other one was the Simpson's rule. And using these methods we could integrate a one-dimensional function or a function which depends only on x over a domain which was from xa to xb. And we had also introduced some other terms, quadrature weights, quadrature points and values of the function f at specific quadrature weights. And using those three terms, we had developed an expression, a general expression for approximate integral, which was equal to, which is f of xi times wi. When you sum it over a series from 1 to r, you get the approximate integral. So today we are going to extend this discussion further. So the first thing I wanted to mention is that we had seen that there is one way to integrate, that is known as trapezoidal rule. There is another way, we can use Simpson's rule. But when we are doing finite element analysis, we do not in a lot of cases use these trapezoidal rule and Simpson's rule for numerical integration. Rather, we use two other schemes. The first one is known as Gauss Legendre quadrature. So this is another scheme for performing numerical integration, and it provides us with significant advantages compared to trapezoidal rule and Simpson's rule. And what are those advantages? We will see that later. So this is very frequently used, and somewhat less frequently used is another method known as Newton-Cotes quadrature. Newton-Cotes quadrature. So these are more popular, and among those the one which is really popular is this Gauss-Legendre quadrature. It offers. So in the remaining part of this week, we will be actually developing the thinking which will help us understand how Gauss-Legendre quadrature works and all the details associated with this thinking. So before we start doing that, I wanted to introduce this notion of natural coordinate system, which is extremely important. Natural coordinates. So in the last class we had seen that when we are integrating from point xa to xb, that is the domain of the element, right. Now in reality this xa and xb, these values can change from, not can change, they will change from one element to other element. So it is a little more tedious to generalize this type of a numerical scheme, because, right. But consider a method where every element has a domain which is ranging from -1 to 1. So the domain is fixed. How that works out, we will see that later. But every element has a domain. The first point is -1 and the last point is 1, all the elements. So in that kind of a system, if I have a numerical integration scheme, it will be easier because I do not have to change my xa, xb and all this thing every time. Okay. So that is where this concept of natural coordinate system comes in. So, what we are doing is that if I have an element and its x coordinates, so this is in the x coordinate system, right, it is in the x system. The first point is xa and the second point is, last point is xb, and the length, so this is my eth element and the length is he, and this is equal to xb minus xa. Okay. Now, I, instead of using this element for doing numerical integration, I want to use a different element. Here, so this is node 1 and this is, let us say, node 2. Node 2. So, right now we will just talk about a 2 noded element, but we will extend this discussion for multi noded elements also. So, here in this node 1 element, in this different element, this also has 2 nodes, but its first coordinate is -1 and the second node is located at +1. Okay. And let us call this, so this was x coordinate, I will call this, what do you call this? Zeta. So, we will call it zeta coordinate system, zeta coordinate system. So, I have an x coordinate system, but I want to use an element which is this long, it has 2 nodes again, -1 to 1 in a different coordinate system called zeta coordinate system. So, my aim is to somehow transform or map this eth element in the x coordinate system to eth element in the zeta coordinate system, such that the first node, which is located at coordinate xa, moves to location -1 and the xb gets transformed to location +1. This is my aim. Okay. So, to do this transformation, I will say there could be a transformation function and what does this transformation function do? It connects zeta and x together through an equation. So, let us say that equation is equal to x is equal to a plus b zeta. Where a and b are unknown constants. They are unknown constants. So, our aim is to figure out what is the value of a and b. Okay. Now, we know 2 conditions about these 2 elements, that corresponding to xa, what is the value of zeta? Corresponding to xa, what is the value of zeta? -1. So, when x is equal to xa, value of zeta is -1. So, it is a plus b into -1. And when x is equal to xb, the value of zeta is a plus, what is the value of zeta? +1. So, this is equal to a minus b and this is equal to a plus b. So, from these we can calculate the value of a and b, which were unknown till so far. So, a is equal to xa plus xb by 2, and this is equal to xa plus xb minus xa by 2, I can write it like this, and this is equal to xa plus he by 2. Similarly, b is equal to xb minus xa by 2, and this is equal to he by 2. So, what we do is we plug these values of a and b back into this equation. So, my transformation function becomes x is equal to xa plus he by 2 into 1 minus zeta. This coordinate system where I have zeta, this is called natural coordinate system. It is also called normal coordinate system. So, the important point is that if I go from one element to other, the zeta element does not change, right. But this mapping function, the transformation function changes because xa changes and he can change. So, any two noded element with whatever values of xa and xb can be transformed or mapped into an element in the zeta coordinate system having first node at -1, second node at +1 and the length being 2, because the transformation constants a and b, they vary from element to element. Okay. So, how does this help? If I can integrate in the zeta coordinate system, then I do not have to, the integration mechanism does not have to change from element to element basis, right. So, a lot of times, in an extremely large number of times, all the commercial codes, they do not integrate in x coordinate system, they actually integrate in zeta coordinate system. And how do we perform this integration? We perform it using these Gaussian Legendre quadrature. We will understand the details later, but all those additions or numerical integrations, they happen in the zeta coordinate system. So, this is very important to understand. So, some other advantages are, that in the zeta coordinate system, it is easy to construct interpolation functions. So, this we have already discussed, and the other thing is that it is easy to implement Gauss Legendre quadrature. So, these are the advantages of natural coordinate system. Okay. Now, we will continue this discussion further. So, the next related topic is, so we had said that it is easy to construct interpolation functions in natural coordinate system. We will see why it is so. So, we will now derive Lagrangian family of So, we will develop a method, very easy to follow method, how to develop Lagrangian family of interpolation functions. So, consider an element, it is having x a first node, second node is x b. So, this is in the regular coordinate system, and let us say that it has several nodes. Let us say it has node 1, node 2, node 3, node 4. So, it has 4 nodes. So, how many approximation functions it will have? If it is a 2 noded element, it has how many approximation functions? 2. If it is having 3 noded function, for Lagrangian family, it will have 3 approximation functions. So, this will have 4 approximation functions. And what will be the order of polynomial for these this element? It will be third order, right? It will be third order. So, these approximation functions, let us call them phi j, which are functions of x j. And what is the property of these functions? That the value of this approximation function is 1. Okay, so phi I x j, and okay, so let me make sure that we get this right. This is x1, this is x2, this is x3, this is x4. So, xa is equal to x1, then x2, x3, x4. So, this xj can have how many values? This is a discrete, the 4 values, x1, x2, x3, x4. So, and phi will be having 4 values also. There will be one phi associated with node 1, node 2, node 3, node 4. Okay. So, the value of phi I, it varies with x, when x is equal to x1, it will have some value. So, the value of phi I will be 1 if I is equal to j. And this will be equal to 0 if I is not equal to j. Okay. So, what does this mean? Suppose I am developing an approximation function phi 1, then the value of phi 1 at first node will be 1 and it will be 0 at node 2, node 3 and node 4. The value of phi 2 will be 1 at node 2, it will be 0 at node 1, node 2, node 3 and node 4. The value of phi 3, it will be 1 at node 3 and it will be 0 at node 1, node 2 and node 4. And similarly, value of phi 4 is going to be 1 at node 4 and 0 at all other nodes. So, this is a property of Lagrangian family of interpolation functions. This is an important property. Actually, it is a property of all interpolation functions. Okay. So, this is an x coordinate system. Similarly, if I have to do work in natural coordinate system, then the length of the element is going to be 2. It will range from -1 to +1, and it will also have how many nodes? If I have 4 nodes in the x domain, then it will have 4 nodes in zeta domain also. So, this is zeta 1, zeta 2, zeta 3, zeta 4. And here I call these functions as psi, just to differentiate, that is all. Okay. And these values of psi depend on psi j, no zeta j, and this is equal to 1 or 0 it is 1 if I equals j and it is 0 if I is not equal to j. Actually, such a function can also be written as Kronecker delta ij, right? That is beside the point. So, this is an important property. So, when we are developing Lagrangian functions, we have to make sure that the values of those functions is 1 at a node associated with that particular function and 0 at all other nodes. This is an important thing. So, in the zeta coordinate system, what does that mean? That the ith function psi I means that it is associated with which node? Its value will be 1 at which node? Ith node. So, this is actually a function of zeta and its value is going to be 1 at ith node and at all other nodes its value is going to be 0. So, this is, and it will be of what order? Suppose the total number of nodes n is equal to number of nodes, then the order of polynomial will be n minus 1. So, its value is going to be 0 at all other nodes except ith node. So, if it has to be 0 at all other nodes, then it will have to be some constant times zeta minus zeta 1, because it is going to be 0 at first node, zeta minus zeta 2, it is not going to be 0 only at ith node. So, first node it is 0, second node it is 0, dot dot dot, and I keep on going till zeta minus zeta I minus 1, right. I keep on going. I do not go till zeta I, because if it is zeta minus zeta I, then it will be 0 at ith node also. And then I continue further, zeta minus zeta I plus 1, dot dot dot, zeta minus zeta n, right. How many terms are these? These are n minus 1 terms, right, because I did not have zeta minus zeta I term. So, this function will be 0 at all other nodes except the ith node, because I do not have zeta minus zeta I here. And this Ci I do not know, Ci is unknown, right, it is unknown, Ci is unknown. What is the value of this function at ith node? At ith node its value is what? 1, and the its value is 1 at ith node. So, we find the value of Ci using this condition. So, psi I at zeta I, so this is first equation, let us call this equation A, and what is the value of psi I at zeta I? Zeta I is what? Ith node. So, it is at ith node psi I is 1, and that equals, if I use equation A, Ci times, what do I do in this equation? I replace zeta by zeta I, right, everyone agrees with this. So, from this equation, in this equation B, there is only one unknown, which is Ci, everything else is known. I know the location of zeta I know the location of zeta 1, zeta 2, zeta 3, all these things. So, I can calculate Ci from here. So, from A and B, the relation for psi I is what? It is looks complicated, but it is pretty simple. In the numerator I have zeta minus zeta 1 So, this is in the numerator, and in the denominator it will be, and I have to multiply this by Ci, which is basically 1 divided by this entire term, right. So, in the denominator I get this. So, that is my function, the definition of function zeta psi I in zeta coordinates, right. This is the definition of zeta coordinates, and I can, using this formula, I can have any approximation function of nth order, n could be 1, 2, 3, 20, whatever. This is a pretty standard formula, and I can easily automate it in the computer. So, a lot of FEA theory, I mean theory is there, but now what we are learning in these lectures is how do we actually automate it using computers. So, that is why this type of definition of Lagrangian functions is easy to develop in computers, because it can be very easily computed, because it does not change from element to element, right. It does not matter what the value of x is and what the value of xb is, because we are in zeta coordinate system, and there the limits are -1 to 1, that is all. So, we will continue this discussion in the next class, and till then have a great day.